Linguistics, chiefly computational linguistics, is extremely complex, but the basic principles can be explained simply. You don't have to be a software developer or a linguist to get the general ideas. And it all boils down to address one question. In the context of language, what does it mean to understand? How is it possible that a mere sequence of characters or letters, or utterance of syllables, is able to express anything within the vast realm of human knowledge and experience? The human ability to use language to allow for complex thought, creativity, and transmission of culture is nothing short of astounding. It is with that passion and genuine desire to produce something of utility and value that I devoted so much time and effort into building this NLP system. Basically, we understand language through two types of meaning, semantic and structural. Semantics focus on meanings of individual words and phrases, even when we use the same word to describe different concepts, which makes the word ambiguous. Structural meaning, or syntax, focuses on the grammatical structure and rules of how words are combined to form sentences, ensuring that they're comprehensible, even when the listener or reader can interpret them in more than one way. While language isn't entirely efficient given these ambiguities, both semantic and structural, these two aspects are essential and interdependent. They work together, syntax providing the framework for meaning, and semantics giving that framework its specific interpretation. My system analyzes sentences in a sequence of stages. First, it looks up individual words in its vocabulary. It also determines whether certain groups of words comprise phrases that are also included as separate entries in the vocabulary. Once these are identified, it collects data on each, its individual definitions, and the concepts in the ontology with which these definitions are assigned, among other types of data. Then it applies this data to structural rules to identify different grammatical structures based on parts of speech. These include noun, verb, adjective, adverb, and prepositional phrases, predicates, participles, and subordinate clauses, until it establishes that a series of parts of speech for each word comprises a single main clause, the basis for all grammatically correct sentences according to the rules. Bear in mind, the grammar rules aren't only prescriptive, which dictate the rules for correct or formal language, but also descriptive, how people informally use language. It covers things like split infinitives, dangling participles, or sentences ending with a preposition. At the same time, it applies semantic rules to determine which definitions of individual words apply within each structural rule tested. The best analogy to this process is a combination lock. Consider a bike lock with 4 dials, each with 6 digits. The number of ordered combinations, or permutations, is 6 to the 4th power, or 1,296. Only one permutation of numbers succeeds in opening it. By analogy, most often just one sequence of parts of speech and definitions in a sentence is the grammatically correct one and the one that makes sense. If a sentence is truly ambiguous, there may be 2 or 3, as in the girl gave a hand to the man. And here we confront a serious problem. Some words in the vocabulary have multiple parts of speech, like well, which could be a noun, verb, adjective, or adverb. Some words have multiple definitions, like the word break, as I pointed out, which has 59. Depending on its length and words used, the total number of possibilities for every part of speech and definition of each word in a sentence could potentially result in hundreds of thousands of these permutations. How can any software handle that combinatorial explosion without crashing? Any software engineer could tell you that there are a number of programming techniques to easily handle situations like that. These techniques are called dynamic programming. Dynamic programming solves optimization problems by breaking them down into smaller overlapping subproblems. The solutions to these subproblems are stored temporarily in memory, so that the software simply retrieves the solution when it encounters it again. This makes sense. Once you have a solution to a problem, there's no need to redo all the work to solve it again. Once all that unnecessary work and all those redundant calculations are eliminated, demands on memory are vastly reduced, and the process of finding the solution is vastly accelerated. Another technique to speed things up is a more common sense principle. The best and fastest way to handle a large, complex job is to divide it into smaller, more manageable jobs. In workplaces, this is formalized as a work breakdown structure, which lists and prioritizes all necessary steps to solve a problem, which also better tracks progress. When the system looks up words in a sentence, it combines them into fragments and analyzes only a few of those fragments at a time, from left to right. If the analysis of any set of fragments fail at some point, those partial permutations that start with it are eliminated, and the system moves on to the next one. In the bicycle lock analogy, it's a little like testing the first two in the combination. You eliminate all the other combinations that don't start with them, then test those first two digits with the 6 possibilities for the third. Do the same for the fourth, and so on until you reach the last dial. Instead of testing a maximum of 1,296 combinations, you need test only as few as 48 to open the lock, 27 times fewer possibilities. In the same way, the system eliminates the unnecessary work of applying rules to permutation that it knows in advance won't resolve into a main clause. In combination with dynamic programming, this is yet another way the system reaches the solution much more quickly. A third technique involves not overlapping problems, but rather a smaller number of different types of problems. This is yet again best explained by analogy. Over 160 million unique organic and inorganic chemical substances are known to humanity. These only the small fraction of which that have been identified or synthesized. All those substances are arrangements of a far smaller set of 94 out of the 118 confirmed elements in the periodic table. The atoms of each of those elements are composed of just 3 primary particles: protons, neutrons, and electrons. My point here, quite simply, is that no matter how complex the structure of a sentence that a user may enter into the system, the types of different tasks in the process of analysis are relatively few in number and are easily identifiable. This enabled me to streamline and modularize the source code to the point that the system most often completes the analysis of the sentence in less than 1 second. A fourth technique involves a foundational observation in Noam Chomsky's theory of generative grammar: the infinite use of finite means. This principle posits that every human language, despite having a limited set of sounds, words, and grammatical rules, allows speakers to generate and understand a theoretically infinite number of unique sentences. The finite means are the limited, though large number of words, and the finite set of rules or grammatical principles for arranging words and phrases into sentences. The infinite use of those finite components is made possible by the concept of recursion. Recursion is the process of embedding one structure inside another, repeating that process indefinitely. In language, this allows for the creation of new complex sentences by building upon simpler ones. For example, a verb is part of a verb phrase, which is in turn part of a predicate or a participle, both of which are part of clauses, all of which are created in iterations of that recursion. Chomsky cites a popular English nursery rhyme to demonstrate this recursion, the last verse of which reads, "This is the horse and the hound and the horn that belonged to the farmer and sowing his corn, that kept the cock that crowed in the morn, that woke at the priest all shaven and shorn, that married the man that all tattered and worn, that kissed the maiden all forlorn, that milked the cow with a crumpled horn, that tossed the dog and worried the cat, that killed the rat and ate them all, that lay in the house that Jack built." This fits nicely for one purpose of large language models, to generate text, though the generation of language patterns is haphazard and doesn't have a formal structure. My system, yet again, does the exact opposite. The finite set of rules it uses are a veritable classification of English sentence structures. The recursion runs backward, progressively applying rules to build a structural diagram of a sentence from a string of words that composed it. Put another way, the same recursion which enables large language models to generate output enables my rule-based system to analyze input. This essentially describes the entire sentence analysis process. My goal now is to use this novel technology in an application on which I've already begun work. It meets the demands for knowledge management, enabling users working in teams to virtually store, retrieve, and update the semantic and syntactic content of sentences within a specially designed database, as well as exercise the abstract reasoning I described in the first video. One immediate use could be for technical or customer support, which requires a centralized, updatable repository of information about products, services, and company policies, and other things that staff can quickly and conveniently share among themselves as needed. To this end, I close with arguments which stress the necessity and opportunity that effective sentence analysis provides, and pertain directly to the knowledge management application I plan to develop. Reasoning depends on understanding statements and determining logical validity and soundness. Understanding statements and determining their logical validity and soundness depend on recognizing their structural and semantic meaning. Recognizing their structural and semantic meaning depends on an ability to resolve ambiguity. Resolving ambiguity depends on effective sentence analysis. In a deductive argument, if any premise or link in the chain of reasoning is false or absent, the entire argument becomes unsound and the conclusion is not proven, even if the logic is otherwise valid. This logical chain, each link of which is entirely sound, highlights the merest fraction of this application's potential. When we consider the overwhelming problems of misinformation and propaganda in today's world, the usefulness of this process to ensure reasoning in business and other affairs becomes clear. This concludes my explanation. Thank you for your attention.